Okay, now that we've gone over all the things that you need to know to start wrapping your mind around aircraft electricity on the most basic sense, now we want to get to where we can actually employ that knowledge in troubleshooting and trying to fix problems that we may find on an aircraft. Now, the first thing that we need to do is we need to be able to measure things. So at first, we're going to talk a lot about different ways that we can measure stuff, from very, very basic to the more advanced like methodologies of measuring what's happening inside of an electrical circuit. Then we're going to talk about circuit continuity and some basic troubleshooting tips with our trainer that's behind me right here. Now, over the years, there have been a lot of different instruments that was employed for electrical troubleshooting. A lot of them were very specific to measuring a very specific thing, such as voltage meters measured volts in a system. It's really simple. The easiest thing to figure out what it does is just simply read the name. It measures volts. It's a voltage meter, right? An ohm meter measures ohms, measures the amount of resistance in a circuit. A amp meter measures the amount of current in a circuit. It's an amp meter. Over the years, though, people began to realize these are really clunky, and they were really big too. A lot of times, especially like you'll still sometimes use ohm meters that are analog, that still have like the dial, and those are used because they're extremely precise. They're mechanical in nature, so you have to like whatever is in that circuit is what you're going to get on the dial. There's no room for like digital error or anything else like that. But for the most part, you're actually going to use a multimeter. Here's a Fluke 289. It's not the one that well, you will use this one. We have 5 of them, but you're going to use one that's a little bit lower grade that's inside the student kits here at the school. But we're going to start by going over the 289 and all the symbology that's on the dial and how we're going to employ it. Essentially, the thing that you need to remember is that all of those old meters, those ohm meters, voltage meters, amp meters, so on and so forth, have been combined into a multimeter. It does multiple things. It's a multimeter. Very, very simple. Okay, first let's start by turning the multimeter on. There's a power button on this one. Some of them, however, it's integrated into the dial. Now this first setting on the far left hand side that says LOZ, that's a low input impedance to try to help detect ghost voltages. The next one up though is pretty vanilla. It's just volts AC, but you'll see that the range is set so that way it goes out to the 4th decimal place on this one. You can go to the next setting where it's millivolts. The next one is our first DC voltage. DC is always dictated or annotated by a solid line over a dash line, whereas AC is always a wave. Now this setting right here is the resistance setting. You can say it's open line or OL right now. That's the one that you're going to live with the most. Next being the diode or capacitance tester. You'll use that a lot. And then now we're into amperage. And you notice it's giving me a warning. That means that we have to move the lead over to the fuse side, so that way in case the meter were to be exposed to a high amperage, it wouldn't destroy the meter, it would just blow the internal fuse. Each one of these is fused differently, so you'll notice that as I change the dial, I also have to move the lead to the appropriate input there at the bottom. But the common always stays the same. Okay, so let's go back to the resistance measurements. It's going to be the most common way that you use pretty much any multimeter. Is just checking continuity of 2 different wires. So here we have a wire that we have good continuity for. You see how low the resistance gets? Is sub 1 ohm. Well, I'm going to insist that you turn on the alarm for your multimeter so that way you can hear that you have good continuity. You notice that every time that the wire touches the lead there, the alarm goes off and lets us know that, hey look, this wire has good continuity from end to end. Another pretty common use for the multimeter is to actually use it for voltage. So here we're going to test the battery for DC voltage. We're going to see if it's charged or not. If it's charged, it should be over 12 volts, and so we're going to take our negative lead, put the negative, positive the positive, and we see we get 12.715 volts in the battery. You can take it away, and put it back together. And that makes a good point. Always take it away and put it back so that way you can verify that your reading was actually true.
Okay, this is a megaohmmeter, right? It is a Fluke 1587, and it's primarily used for doing installation testing. The most common usage for this is trying to figure out the health of electric motors, hooking up to one phase to ground and seeing like what its installation is, and then going through other phases and making sure that all of the phases read about the same. Now, there's a lot you can do with a megger, and that's another thing. Very few people ever call it a mega ohm meter, except for like in the book or whatever. Most people just refer to it as the megger, and that's what it is. And so we're going to go over how we can use the mega ohm meter and how we can employ it. It has a lot of different uses, and they're like the further you get into aviation, you'll find a lot of people have very creative ways to employ a megger.
Okay, so this is a megaohmmeter. Notice that it's set to installation test. We're going to test the resistance on all three phases of our AC generator on our trainer. It's an AC motor that turns our alternator for the trainer. So it's hooked up to the first phase. We're going to press installation test and hold it until we get a reading. Notice that it's greater than 550 mega ohms. That phase is good. So now we're just simply going to keep the ground in the same place. We're going to move it over to the next phase, and we're going to just repeat the process, and we should have something very similar. And there we go, greater than 550 mega ohms. So on a three-phase motor, we should have one more phase to check. So we're going to move it over there, clamp it on, hit the installation test, and we should get 550. So that's a classic way to use a megger. Here's a little bit more creative way. We've got the megger that we're doing an installation test, so it's sending voltage down a wire that's been shorted. We're combining that with a ultrasonic imager, and as the wire arcs, it's starting to make noise. As it makes noise, the ultrasonic imager picks that up, and it highlights the area visually where the short's at. So you can imagine how useful this would be in trying to find a short somewhere in a large airplane.
All right, this is a handheld oscilloscope, or an O-scope. Now, oscilloscopes have come a very long ways, and nowadays you'll see some of the more advanced avionics guys come out and actually use an oscilloscope to figure out what the signal voltage looks like coming from one device to the other, to figure out if the computer itself is actually sending the right signal to make a thing happen. Now, for the most part, this seems to be like a dying art. Back in the day when bench avionics was a really big thing, the oscilloscope was a very common item that you'd see around aircraft, and you'll still see them used. But for the most part, nowadays, like your line and heavy maintenance, you're doing a lot of like wire work. You're trying to figure out, is everything connected? And if the box is messed up, you're not opening up and probing a board to try to figure out like if all the components inside of a circuit card are actually working correctly. For the most part, you're just swapping out boxes. However, we don't know where you're going to go with your career, so we're going to try to prepare you so that way you know how to use an O-scope, and at least know the basic functionality of it, so that way you can employ it if you're ever given the chance.
Now, oscilloscopes compare two things, time and voltage, and that results in it being able to graph. You'll have time on one axis and voltage on the other. As that voltage and time changes, you get different waveforms. You can have square waves, you can have sinusoidal waves, so on and so forth. All right, here we're going to look at a sinusoidal wave coming off of a microcontroller on our Arduino. Whenever you're going to look at this, you're generally looking for signal voltage coming from like a sensor or control input or something like that. Now that signal voltage has a range of where the signal should be at its lowest voltage point and where it should be at its highest voltage point. We can use the O-scope to not only see how long the signal voltage is taking to go from bottom to top, but we can also see what range it's going to on the very lowest to the very, very highest. If it's out of range, then we're not going to get the same type of movement on the aircraft that we would expect, and that could be part of our problem. Now we're going to deal with these a lot more in advanced avionics. This is just to kind of give you some familiarity with what O-scopes do and what they look like.
All right, this is a time domain reflectometer, or a TDR. what it will do for you is tell you how long a wire is. There's a lot that TDR can do, but effectively the way we're going to use it here is we're going to shoot a wire and we're going to see how long it is. Now you would say, like, why do I want to know that? Well, for small airplanes, you're right. Like, you can simply like open a panel or cock your head sideways and see the end of the plane. But let's say you're working on a 747 and you're up in the cockpit. Well, do you really want to like walk that entire plane to try to find where a wire break is? Or would you rather have an idea of about how long it is, and then you can go to the manual and figure out a junction to start your troubleshooting there? So a TDR, we're going to show you how to use it. Don't expect to use it just a whole lot. Even in places that have TDRs, they usually have a specialty team that comes out to you, because they're pretty delicate. Okay, so now that we have the theory down, we understand electricity, at least at a pretty high level, and we know the tools and we know how to employ those tools, let's talk about a basic test that will kind of get us started on our troubleshooting journey, that like we can employ. And you'll use this is like, I will be honest with you, we're going to show you a lot of cool stuff. The 90% of the time, these are the types of tests that you're looking for. Modern day aircraft, like heavy commercial aircraft, most of the time, if you have a box failure, you have an LRU that fails, you're just going to take that LRU out and you're going to put a new LRU in. You're not necessarily going to do anything super duper crazy. Most of the crazy stuff comes in whenever it's like all the regular stuff has failed, and they're going to call in like, you know, a top, you know, troubleshooter to start trying to play all these kind of crazy games. But for the most part, you're going to live in the land of continuity checks, or you'll hear ring outs as another term for it, because the meter rings. Like whenever you turn the audio alarm on, you hear it beep, which is really useful for a lot of different reasons. But like, let's just talk about continuity checks, and we'll just get started there and we'll kind of progress on. All right, continuity, what is it? Continuity means continuous. It means that the electron can start its journey from its power source and go all the way through the circuit and come back in. All right, if you have that, then you have continuity. If you don't have that, then you don't have continuity. It's real simple. All right, so here we have an example of a circuit. Notice the switch is open. Since the switch is open, then we don't have continuity. All right, now it doesn't mean that it's broken, it just means that it's just open. All right, if we were to close the switch, like so, then we have a continuous circuit. We have continuity. Now, that means that an electron can come out of here, go through the switch, through the lamp, and then come right back in here. It also means that if we were to take our meter, this is going to be our meter, and we're going to take a lead, we're going to tie it right here, and take another lead, tie it over there, and we were to set it to ohms, it would show us how many ohms are in that circuit. Usually it's not very much if it's done correctly, unless this is like some sort of like high demand thing, like a heating coil or whatever. So you say it's 5 or 6 ohms, call it a day, all right? Anything above 8, then you start running into questions like, okay, well, what's going on here, unless it's like a really long run. Like if you're going from one end of a 737 to the other end of the 737, you're gonna have 20 ohms, all right? But for most circuits, like you're looking at like 5 or 6 ohms or so, all right? If you have the audio alarm turned on onto your meter, which I'm going to demand that you absolutely do in here, you'll hear a beep, because it's saying, hey, look, you got continuity, beep. All right, so let's say what happens if you were to have a break in a wire. All right, we're going to draw the thing up. Something happened right there. What happens to your meter? What's it going to show? Well, it won't beep. And it's going to show like infinite ohms. It's just like 0, 0, 0, 0, 0. Like, you know, it'll say OL on there, which means it's like it's overloaded. It's out of limits. It's completely gone. Like there means that what's happening is that you technically still have continuity, but it's through the atoms in the air, which is like infinite resistance. So you'll never get this lamp to come on. And so therefore it won't ring, it won't beep, it won't do anything. And you know that you have a problem. And you know that the problem is a continuity problem. It's not a voltage problem, it's not anything else. It's literally just the wires aren't connected. So let's talk about like what are some of your common culprits whenever you fail a continuity check. Well, for one, something's not connected right. Like I can't tell you how many times after some sort of rework, especially wiring rework, where continuity basically says, hey, look, you know, these things aren't connected, and what you end up doing is like you'll say like, oh, it's in this connector right here. We know through the wiring diagrams that it connects to these connectors over there, and you start ringing wire to wire. They call it like end-to-end ring outs, where you just go through the whole thing, and eventually you'll end up finding you won't be just one wire that's not ringing. It's two wires, and it's because they're swapped. And then next thing you know, you can verify that by simply like going from pin A over here to pin D over there, and it's like it's got continuity. It means that you just need to move that contact, put it in the right spot, flip them around. Not a big deal. Sometimes, especially after some sort of like disaster that's happened on the airframe, that means that the wire is physically cut. This is something that we ran into all the time on the floor at Boeing whenever we were building the 737 MAX, because what would end up happening is that you'd have a lot of people working in different places or whatever, and somebody would cut a wire by accident. That has a lot if you're not using a wiring spoon to spoon out the wire that you're trying to trim or whatever. Or during installation, something would get pinched because it wasn't quite put in the right spot. And that's what we were there for. We were there to do quality assurance to make sure that like everything was where it was supposed to be. So we would ring these wires, it wouldn't ring, and then we would go and we would start to look for it. And we would find that, yeah, sure enough, there's a wire that they got cut, pinched, whatever, or it was directly touching the side of the airframe. It was ringing the ground when it was supposed to. And so that's another obstacle. One of the trickiest ones, however, and this is one that you will see, is corrosion. You'll have, if you think like go back to your 737, if you're looking, to the aircraft forward, and you have your big wall full of your hydraulic stuff, you'll have wire runs that go through there. Well, in those wire runs are connectors. Those connectors get exposed to all sorts of elements. Those elements come into the connector, and we're going to see in our corrosion class that one of the key things with corrosion is having electricity, having some sort of like presence of water, some sort of medium, and differential metals. And like those three things combined together always creates corrosion. We have all three of those things inside of a connector that's exposed to the elements. So you'll end up having a corroded connector. Now, this gets tricky because as the plane lands, a lot of times it jostles everything. That little bit of a bump on a connector that's tied in and it's just barely making it, sometimes can like jostle it loose or connect it back, and you might get an intermittent fault. Or you may get like, it's an open, it's just like there's no fault whatsoever. And you start trying to troubleshoot through, like trying to figure out where it's at. And sure enough, you come to a connector and it's all corroded up. And next thing you know, you're just taking the contacts off, put new contacts in, or maybe replacing the connector or whatever, what have you. But ultimately, you're going to find that through a variety of ways. But one of the main ways is through continuity checks. And so that's what we're going to go do. We're going to give an example of a continuity check. And then in class, you're just going to do a bunch of them. So that way you're very, very familiar with taking the wiring diagram and then working with a buddy to try to like troubleshoot through where these discontinuities on the aircraft are.
Okay, so here we are. We're going to set our meter up for continuity checks. So we're going to turn it on. This meter, we have the on button, like we said before. Yours should just be a dial. Make sure it's set to the ohms and turn your alarm on. So that way you can hear the alarm. You want to test it. Always test your meter. Make sure it's working, because the last thing that you want to do is do a lot of troubleshooting, thinking that everything's okay, just to find out that your meter wasn't working or the alarm wasn't on. Next thing you know, never ever work on an electrical circuit with power applied. This one doesn't have a switch, so we're going to actually have to physically remove the battery. That's what I'm doing right now. Now, there are situations where you're going to be wanting to troubleshoot power. That is something that we'll cover later on. For right now, don't worry about it. Simply for your continuity checks, make sure that the battery is disconnected and the airplane is not running, and it's not connected to ground power. Those are the three places that you can get electrical power on an aircraft. You want to make sure they're all disconnected before you start shooting wires, because if there is a fault on the aircraft and you ground it out, you're going to get an arc, and those arcs can be pretty devastating, and you don't want your hand to be the one that gets devastated or get electrocuted or something like that. Alright, so a little quick meter check, and we're going to give you a little demonstration. So we're going to go from one shunt to the other shunt. We know that they're directly tied together, so we should have continuity. So we have very low resistance there, I think it's like sub 1 ohm, and the alarm's going off. So we know that we have continuity through the shunts. So here's a place that we should not have continuity. So if we remember the way the relays work, our relay doesn't have power to it, so it should be open. But notice when we check the switch current, it actually rings, but the other side doesn't. So that relay's probably good. We can swap it on and off and see if we get continuity based on different configuration. Okay, here we have a circuit breaker that is ringing. We're going to pull that circuit breaker, and you can see that it goes to an open line. The ring stops. Push the circuit breaker back in, ring comes back. This is like a basic troubleshooting technique that you'll do 1,000 times. You'll end up having a plug pulled, your meter hooked up to it, and somebody pushing the circuit breakers in the cockpit on, in or out, to try to figure out where the break in the line's at.
Let's look at how our wiring diagrams integrate with the continuity checks. So let's say we wanted to, we had a problem with our angle of attack indicator, right? And our suspicion, for whatever reason, was that the altitude shift box over here wasn't sending power to the angle of attack indicator. So what could we do? Now, I don't know where P400 is right here, this guy, but let's just say it's in an inaccessible spot. So we have this twisted pair that's indicated by this little infinity looking symbol there that is pinned out on E and F on this side and W and B on the other side. So let's do a thing. Let's ring through it. We're going to go over here to pin G, and we're going to go to ground. All right. Kind of did that backwards, but yeah. So we're going to ground that out. Take the connector off, put a pin on, or put our lead onto G, and then clip it off to a grounding point somewhere on the aircraft. We would then come back to M32, take this connector off, PE94, and we would take our meter. Remember our meter? One lead's going to go to ground. So now you have a connection between these two, right? And you're going to have another lead that comes off and pins to E. If we get a ring, if we show that we have continuity down from pin G all the way down to pin E, then we can go on to the next thing. And we want to highlight that just like we did, so that way we know that this one run is good. But then now let's say if we go to pin F and go to pin H, same thing, we just move this lead over and move this lead over, and we don't have continuity, then we found our problem. And for whatever reason, this wire run right here is the problem. So that we would then eventually have to access this area and shoot either direction to try to figure out where the breakdown is. But that's how, kind of a simple example of how we would use continuity checks to troubleshoot. And you're going to do several of these whenever you get into class. And all, troubleshooting is not really that difficult, and it's actually a lot of fun. A lot of people are more scared of it than anything else. They see electricity and they freak, and they think they're going to get hurt. They think that they're going to they're going to break something, or they think that they'll never be able to figure out of it because they're just not that sort of electrical person. That's like some sort of like crazy math wizardry. And it can be, but for the most part, it's you and a multimeter and a wiring diagram and just troubleshooting the problem. A lot of times, like, it's a lot of fun. It's like figuring out a puzzle, but it's one that you're getting paid for, and one that matters, because the airplane can't fly if it's not, working properly, and you're the one to fix it. So don't run away from troubleshooting like opportunities. Embrace them. Jump right into it. Most of the time, you're gonna hit something, and you're gonna have no idea what's going on. You're gonna look at things that you're gonna see like relays, and you're gonna be like, well, how do I get past this relay because I know that's not on? Do I need to apply power and actuate the relay, then check it again? And you're gonna start to really start to flex that muscle as you start to have to deal with coils and motors and lamps and all kinds of random electrical devices that stand in your way to really getting after the problem. That is all extremely good for you. Go and just tear into it. Make a bunch of mistakes. Fail fast. Fail often, because that is how you learn. The next thing you know, whenever someone says hey, look, this thing won't work, or this problem's going on, you're like, oh, that's no big deal, I've got that. I've seen it way worse. I've seen people spend literal weeks troubleshooting electrical faults, and then I was the B man on the team, just running around holding a meter or running around with the radio and trying to help them figure out what's going on, and I learned a ton. Jump into it. The better mechanics are the ones that proactively, just aggressively go after hey, look, here's this work, apply yourself. Here's some work, apply yourself. That will really get you further than anything you're gonna learn in a classroom, anything that you're gonna learn in any sort of like lab or anything else like that. Just by hands-on experience, being very proactive, getting after troubleshooting and taking care of faults as they show up.